We conclude this unit with an introductory study of optimization for functions in multiple variables. For now, we're going to simply look at the general ideas of finding extrema, which is maxima and minima, of a function of multiple variables. And as we go through the last couple of units in the course, we are going to look at how we identify these with formulas. For now, it's just the ideas we're going to introduce. So again, there's so many references back to our first term. We're going to be distinguishing between local extrema, local maxima and minima, and global. So a point will be a local extrema, max or min, if it's not on the boundary. So again, we're going to throw away boundary points as local extrema. And what makes a point more extreme than its neighbors is that its value is always larger than or possibly equal to all the points in some region around where we are. And of course, that would be for a maximum. If we're looking at a minimum, we would have something, our value would always be less than all the values of the function nearby. Again, that's pretty much what we saw in single variable calculus, except we had just one variable in the input side. We distinguished those local extrema from global extrema by throwing away that nearby condition and saying our point's at a global max if the height of the function is larger than or possibly equal to all other points in the domain. If at this point we reach the highest height, possibly tied with somewhere else, but the highest height of anywhere in the entire domain, that would be a global extrema. What we're going to see as we go through this study of optimization is that local extrema are fairly straightforward to identify with calculus. Global extrema are sometimes easy to distinguish in certain conditions from diagrams or from formulas. But in general, the question of identifying and proving that a point is a global extremum is quite challenging. Local would be much more doable. Just to introduce this topic, let's look back at our favorite simple function of simple nonlinear function here, f equals x squared plus y squared. And again, this is our parabolic bowl shape. And we've studied this both in its surface view and its in contours. And I'm going to go through this fairly efficiently. The deriving of the contour diagrams is something we've seen before. We're going to go out to 2 and -2 and -2 and 2 in both the x and y directions. If we let z equal 0, just to remind you, if z is equal to 0, then 0 is equal to x squared plus y squared, and that's just a point at the origin. The only point that satisfies x squared plus y squared equals 0 is a single dot in here, and that's at height 0. If we had z equal 1, we would have x squared plus y squared equals 1, and that's a circle, radius 1. And we'll sketch that out here. Oh, sorry, I'll do those in green. Oops, 1, 2, 3. There we go. So that would be our circle of radius 1, and it corresponds to a height of 1 on the surface. And we saw a few other contours earlier. If we pick z equal 4, we would have 4 equals x squared plus y squared. And remember, this is r squared on the right. That's a circle with radius 2. So this particular contour here is at height 4. I'll draw that outside, actually. I think we'll need the room. And then the last two contours that we were asked for at 2 and 3 would be somewhere in between here. So we'll sketch those out. And do that. There we go. So 2 and 3, 4. And what we can also imagine is that there's other contours further on, 5, 6, and 7, and so on. In fact, we'll talk about the point at the edges in a moment. So we draw the contour diagram, and before we get to the questions of optimization, let's just flash back to a topic we haven't seen in a little while. Draw the direction of the gradient vector at several points on the contour diagram. So let's pick a point here, and maybe a point over here somewhere. And remember what we know about the contours in relationship to the gradients. The gradient points in the steepest uphill direction. And more detail for us in relationship to the contour diagram, the gradient is perpendicular to the contour. So if you pick a point on this contour and notice it's downhill, up, 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 because the heights are getting larger, the Z values are increasing as we move out from the center, the gradient at this particular point here would be perpendicular to the contour and pointing outwards. Likewise over here, that would be the gradient at this point. And we could pick a point down here as well. On the one contour, again, it'll be pointing uphill, steepest direction, and it'll be perpendicular to the contour. From the contour diagram, let's talk about the identification of global maxima and minima. And what we're going to do to make this feasible is identify a limited domain. We're going to limit it to the square -2 to 2 in both x and y. So let's take a step back here. I think from the diagram it's quite clear that 0, 0 is the lowest we can ever reach. Every other point has some z value that's larger than 0. Only at the very, very center point here at the origin are we going to have a value of 0, and it's impossible to have negative values for our function, so the global minimum is easy to identify. The global maximum is maybe a little trickier, but if you think this is the bottom, as we move outwards we increase. I'll take a look and think, where would those maxima occur? If you said in the corners, you're absolutely right, because we want to get as far away from the center. That's going to maximize our x squared plus y squared. Or I want to get to the highest contour I can see. This contour here is at height 4. Just follow it around. All these points have height 4. But if I move a bit out this way, towards the corner, I get to height 5, then 6, then 7, then 8, and so on. And the maximum value would occur at that corner, but because everything's so symmetric, we would, let's do it with an x here. All of those x's share the property that they're the global maxima on the square. Notice we are using the boundary here to define the maxima. If we were allowed to go outside that boundary, we could get higher values still, but on the square that we can see, those points are the highest we can reach. Every other point will have a lower value than the function at those points there. And it's worth noting, what is the function value there? Well, f of 3, 3 would be 3 squared plus 3 squared, which is 18. So we could actually draw a contour that just touches the corners here, and it would be at height 18. And we're pushing ourselves as far as we can towards the corners to reach that contour just at the boundary that we've defined. It's important to notice the distinction here. The global minimum is somehow in the middle and is a special point of the graph naturally. This parabolic bowl shape has a minimum here no matter where we put our boundaries. Whereas these maxima on the boundaries, they're not a property of the function. The function would keep going higher and higher if we let it. They come as a result of imposing a boundary on this function. And it's a combination of the function and the boundary together that make those corner points global maxima. So here we go. At 0, 0, we have the global min with f of 0, 0 being equal to 0. And at 3, 3, at minus 3, 3, at 3, minus 3, sorry, 2, whoa, where did I get that from? My apologies on the last page. I don't know where I was counting from. Let me just go back and correct that before I forget. This would be 2 and 2. And this is the kind of thing I would catch in a lecture a little more quickly. My apologies. 2, 2 is 4, 4 is 8. So we'll just erase those. There we go. Ta-da! My apologies for that earlier error. So those corners would be at height 8. These are all global maxima. They all share the same height at the same f equals 8 height or value. Going back to the idea of contrasting the points that are sort of natural minima or maxima versus those that are imposed by the boundary, the global minimum, that point at the center, if you think about our condition that the gradient is perpendicular to the contour, but the contour is a point. Here we hit an interesting combination. How can I draw a line in any particular direction if I'm perpendicular to a point? How do I point in a single direction? Well, the answer is we can't. So the global minimum is somehow a special point in terms of the shape of the surface. It's also special in terms of how it implicates the gradient. If the gradient has to be perpendicular to the contour, but the contour is a single point, that implies that no direction for the gradient can be selected. No single direction, but no direction in particular can be chosen. Well, what's the only vector that we know that has no direction to it? The gradient that we're looking for here is the zero vector gradient. So every other point, we won't have this vector here. All the other points, absolutely. I have a contour, I can go perpendicular and uphill, I'm good. Any other point I pick on the surface, I can say, here's the direction of the gradient, here's the direction of the gradient. But at a local minimum, that particular one point that is lower than anything else in its neighborhood, the gradient can't be defined because the contour is just a single point, that one point that has that lowest value. And as a result, the gradient at that point has to be a zero vector. So what we're sneaking up on here is some kind of idea of a test for what distinguishes this point, the global minimum, from all the other points that are not local or global extrema. And it's going to have something to do with our gradient.